Here's the solutions for differential equations in physics. Some of these things come pretty much straight out of your notes, so I follow along as needed. Number one, we have a drag force on an object, which is directly proportional to the square of the object's speed. So that force of drag is directly proportional to the object's speed. And we know from physics that if that's the only force here, then mass times acceleration is equal to kv squared. And now I'm going to turn this into a differential equation. And this is part A. Write a differential equation that could be solved to find the velocity as a function of time. So I'm going to do that by replacing A with dv dt. I'm going to also divide m over to the other side because I think that makes it a little nicer. So dv dt is equal to k over m times v squared. And that is the differential equation. That's the answer for part A. That's the differential equation that could be solved. And then in part B, we're going to go ahead and solve it. And our initial condition is that the velocity at time 0 is, we're just going to call it v sub 0. That's my initial condition. Alright, so I need to separate my variables here. So moving this to the other side, that's v to the negative 2 dv is equal to k over m dt. I think it's always a good idea to leave any constants you can over here on this side, because this side's usually just easier to deal with. The antiderivative of v to the negative 2 is negative v to the negative 1, just the reverse power rule. Antiderivative of k over m, which is a constant, is k over mt plus c. I just need to, I suppose you could rewrite it like this, but it'd be nice to have it solved v equals. You have to be careful that you don't violate any rules of algebra here. I'm going to move the negative to the other side, and I'll rewrite that as 1 over v. That's negative k over mt, and then that plus c, I can still write that as plus c, right? I can take being multiplied by negative 1 since I haven't solved for it yet. And then here I'm going to flip both sides, so that turns into v. Now when I flip this side, I can't flip them one at a time. I have to flip the entire thing, and you're breaking algebra if you don't do this. The c has to show up as the plus c down here. It can't be plus c out here. It's not the same. And then I know that at time 0, when t is equal to 0, this is v sub 0. That'd be 1 over, that whole thing would be 0. So that means c is equal to 1 over v sub 0. And that means my solution, finally, is v is equal to 1 over minus k over mt plus 1 over v sub 0. That is the solution. And then we want to sketch graphs of position, velocity, and acceleration versus time. We're just sketching here, so I'm not interested in you doing any crazy amount of work. Position versus time starts out at some initial position of 0. Velocity versus time starts out at some initial velocity v sub 0. And acceleration versus time, well, I'll think about that in a minute. So what would this look like? Well, it starts out, I'm doing this one first because this is the function that I've been thinking about, right? So let's see. As the t values get bigger and bigger and bigger, this turns into a more negative number, and it will overpower this. So eventually you could think about what happens as t approaches infinity. We would get 1 over infinity. So this is going to go to 0. That will go to 0. The acceleration graph is just the slope of this. So the acceleration is going to start off as some larger negative number, some negative slope, and it will get closer and closer to, the slopes get more and more close to 0. And then the position, it starts off at this position, it starts off with a positive slope, but then the slopes decrease towards 0. So those are just sketches of what that would look like. And that's all we're interested in here. In number 2, a little bit more complicated because we have two forces here. We talked about this in class. I'm not going to throw any fancy physics at you on our assessment, but here the net force would be the gravitational force is winning versus the air resistance force, which is BV. So in part A, draw a few free body diagrams. So the free body diagram would just look like we talked about this in class. The gravitational force would be winning, the air resistance force would be losing. So it would look something like that, but you're not going to have to do this on a calculus assessment. AP physics students, of course you would. Write the differential equation that could be solved to find the velocity of the object as a function of time. So now I want to turn this into that differential equation. So sum of all forces, that's mass times acceleration, equals mg minus bv. I'm going to replace this with the dv dt. Acceleration is the same as the derivative of velocity, and I'm also going to divide through by m, so that makes it a little easier to deal with. Then I'm going to separate my variables. Because I can only separate by multiplication and division, I have to divide this entire thing to the other side, as unpleasant as that might look. And then on the other side, I just have dt, all by its lonesome. And then the antiderivative of this is in fact just a linear, this is constant, this is a constant, so it is just a linear factor of v. So the antiderivative will be, so g minus b over mv. And then I have to divide by the linear, the multiple on the v. So dividing by negative b over m is the same as multiplying by negative m over b. Right? If this had been minus 3 here, then I'd have a minus 1/3 out here. So just flipping that. And then the antiderivative of dt is t plus c. Before I can do the exponentiation game to get rid of this, I need to clear anything out here to the other side. So I'll multiply both sides by negative b over m. So natural log g minus b over mv is equal to minus bt over m, and then multiplying that by a constant, still just a constant, haven't solved for that yet. And now I'm going to exponentiate, so g minus b over mv is equal to e to the minus b over mt plus c, which can come to the outside. Still like to solve this for v, so I'm getting there. Quite, so I would add this to that side, and I would get b over m times v is equal to g minus c e to the negative b over mt. And then I would divide both sides by b over m, which is the same as multiplying by m over b. So there it is, but I haven't solved for c. I suppose I guess that's part D. Maybe I'll just do part D right now. since I have it right here. So part D is the one that says at time 0, the velocity is v sub 0. So I'll plug that in and see what that looks like here, see if I can solve for C. So at time 0, the velocity is v sub 0. So that's m over b times g minus, if I plug in 0 here, this is just turns into 1. So I get g minus c. So solving this for c, let's see what we get. So I could bring that to the other side, so that'd be v sub 0 b over m equals g minus c. So c is equal to g minus v sub 0 b over m. That's my c. All right, so that's kind of ugly looking, isn't it? But maybe we can clean it up a little bit, find a better way to write this. It's g minus, the c is g minus v sub 0 b over m times e to the negative b over m t. Can I do all right there? I think I'm good. And you could, I don't know if it's worth it to do it or not. You could clean this up some, because you see, if you distribute this and maybe factor a g out, there's things, I don't know, maybe the nicer way. Maybe I'll just leave it like that, though, and let you toy with that if you want to. Now, part C asks, it says the object will approach a maximum velocity, often called its terminal velocity, or v sub t. So there's two ways to do this. One may be more calculus kind of way. So the terminal velocity is the velocity as time approaches infinity. Right? So let's look at this. Here's our velocity function. What happens as time approaches infinity? As time approaches infinity, then this would be e to the negative infinity. E to the negative infinity is like 1 over e to the infinity. So this is going to go to 0. And this is just a constant. So constant times 0 is equal to 0. So this whole part gets wiped out when t approaches infinity. And my terminal velocity then is just mg over b. And then for you physics students, there's another way to do this, going much sort of higher concept way of doing this. And I think this is accessible to calculus students who are not in physics too. When does the maximum velocity happen? Well, maximum velocity would happen, or constant velocity even would happen, when acceleration is 0. So you could go back to ma equals mg minus bv and say, here at terminal velocity, the acceleration would be 0, right? The velocity is plateaued. There's no more acceleration. So that means that 0 would be equal to mg minus bv for the terminal velocity, and that terminal velocity would then be mg over b. So same answer either way. For physics students, I would like you to think about it like this for sure, but nice to see it both ways. And then we're going to sketch the graphs of these things. They're going to be really similar to what we saw in number 1. So position versus time. Similar, I guess, but not the same. So position versus time, velocity versus time. Here we're dropping something with air resistance, so that's going to start at 0. And here's my terminal velocity. So it's going to basically do sort of an upside down exponential decay toward the terminal velocity, and then acceleration versus time. You can reason what the shape of this is, I think, by looking at this and just thinking calculus. Acceleration is the slope of velocity. Starts out with some positive slope here, and for physics students, you might think about what is that starting value. Well, when v is equal to 0, the acceleration is just g, right? So that would be 9.8. And then it decays off to 0, right? And the acceleration, when you reach the terminal velocity, then the acceleration is 0. Now, you might be thinking, like, reach terminal velocity? According to these models, you never really reach terminal velocity. You just get really, really, really close to it. In reality, you really do get there, because we cannot measure these things with infinite precision, right? And then thinking about displacement, if we started from 0 and we took down to be the positive direction, which I think kind of makes sense, right? It's going in the positive direction, then it starts off looking like something that would have a straight line velocity curve, which would be a parabola like this. But it flattens out and eventually just has a constant kind of velocity. So it starts out increasing like this and then gets to a point here where you just reach the terminal velocity and it just turns into a straight line, right? So here, after you reach VT, this is just straight. So there you have it. And then the last of these, this is just more to think about, really. We talked about this, again, we talked about this in class, so I'll just review that. With Hooke's law, an object on a spring, the spring force is equal to negative kx, and force is equal to mass times acceleration. So acceleration is equal to negative k over mx. If we're going to write the differential equation that could be solved for position as a function of time, well, acceleration is the second derivative of position. And then I think I suggested to you, what kind of function is there whose second derivative is basically the same as what you started with, but with a multiple, a negative multiple of itself? And that kind of function is a sine function or a cosine function. So this is part A. Part B, a sine or cosine. Either one would do. And that's because the second derivative of sine is negative sine, and the second derivative of cosine is negative cosine. That's what we're looking for. A function that when you take its second derivative, you get a multiple of the original. And then sketch graphs of position, velocity, and acceleration. Well, they're all sine and cosine functions, so that means the position versus time. Let's say we started with, sometimes it makes sense to start with a cosine graph, because you could imagine that you have a spring and you pulled it back some to this maximum x, and then it goes doing, 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 like that, right? And then the velocity versus time graph, I'm not scaling any of these are just sketches. The velocity would be the derivative of that, which starts out at 0 and then goes negative, and then it's 0 here, and it's 0 here, and it's 0 here, and it goes negative first, then positive, and then negative, positive, and so on. This is a negative sine graph. If this is cosine, this is going to be some negative sine graph, and then the acceleration graph is going to be the derivative of this, or the second derivative of this, or in other words, a negative cosine graph. Let's try to make it look like it has the same period here. So, like that. And it makes sense, especially you physics students, I want you to think about this, that Hooke's law would in fact give us position that oscillates back and forth like that. Because, you know, you pull something back on a spring and let it go, that's what happens, right? It bounces back and forth between them. And it does, in fact, if you thought, oh, I wonder if that's like a sine graph. Yes, it is, or cosine graph.